Hi, my name is Rebecca Muller. In this lesson, we will define the trigonometric functions of a right triangle. Let's begin by looking at some specific objectives. We're going to look at basic concepts of trigonometric functions, applications of right triangle trigonometry, and complementary angles and cofunctions. The first thing we need to do is to set up a standard way of looking at different angles and lengths of sides in a right triangle. Let's look at that now. Our standard labeling will be given when we have a right triangle where our right angle is here at vertex C. Notice we have the other vertices labeled A and B. The angle next to vertex A is labeled with a Greek letter alpha. The angle next to the vertex B is labeled with Greek letter beta, and next to C we use gamma. The side opposite angle alpha is going to be labeled A. Notice that if we look at the two rays, the two line segments here, these rays make up that angle, then this would be the side of the triangle which is not included on those rays. The side opposite angle beta is labeled B, and the side opposite angle gamma, which is our right angle, is labeled C. Now we need to define the 6 trigonometric functions of a right triangle. Here we'll look at right triangle-based definitions of trigonometric functions. Let's let theta be an acute angle in a right triangle. Then the 6 trigonometric functions of theta may be evaluated as follows. The sine of theta is going to equal the ratio of the side opposite to the hypotenuse. The cosine of theta is equal to the side adjacent divided by the hypotenuse. The tangent of theta is going to equal the side opposite divided by the side adjacent. The cotangent of theta is equal to the side adjacent divided by the side opposite. Secant of theta equals the hypotenuse divided by the side adjacent. And cosecant of theta is equal to the hypotenuse divided by the side opposite. Now, we're going to look at these definitions by considering the following right triangle. In this triangle, you'll note that we have our vertices labeled A, B, and C, where C is the right angle. The hypotenuse of this triangle has a length of 25. Notice that the side opposite the angle theta is equal to 24. And we're not given the length of the third side of the triangle, and we've labeled that with a B, since it's opposite the angle which has a vertex at B. We're going to use the Pythagorean theorem in order to find that value of B. And let's recall that Pythagorean theorem is equivalent to C squared equals A squared plus B squared, where C is the length of the hypotenuse. Now, we can begin by solving for B squared by subtracting A squared from both sides of the equation. We get C squared minus A squared equals B squared. Let's now substitute in the values for C and A that we were given. That is, C is equal to 25, so we'll have 25 squared, minus our value of A is going to be 24 squared, and that's going to equal B squared. Now 25 squared is equivalent to 625. 24 squared is equivalent to 576. Performing that subtraction gives us a value of 49. And now the value which when squared gives us 49 is going to equal 7, and we only have to take the positive value because this is the length of a side. Now, we then have that 7 is going to be the side adjacent to the angle A. Let's now use those definitions for the 6 trigonometric functions in order to find those values for the angle theta. Recall that what we are given is that we have a triangle where our value for the side opposite is equivalent to the value 24. The value for the side adjacent is equivalent to the value 7, and our hypotenuse is equivalent to 25. Let's begin by finding the sine of our angle theta. Now, looking back at those definitions, you may recall that that was equivalent to the ratio of the side opposite to the hypotenuse. And so we can label that 24 divided by 25. To find the cosine of theta, we're going to take the ratio of the side adjacent to the hypotenuse. That will give us a value of 7 over 25. To find the tangent, we're going to take the value, which is the side opposite, and divide by the side adjacent, giving us a fraction 24/7. Continuing on, let's look for the cosecant of theta. That is defined as the hypotenuse divided by the side opposite, so that's going to equal 25 over 24. The secant of theta is defined as the hypotenuse divided by the side adjacent. That will be 25 divided by 7. And the cotangent of theta, defined as the side adjacent divided by the side opposite, is going to equal 7 over 24. Now we're going to try another example. For this example, instead of being given the lengths of the sides, we're actually going to be given an angle for the triangle. Let's do that now. We want to evaluate the 6 trigonometric functions of theta equals 45 degrees, and we're going to then support our answer using a calculator. To begin the problem, we need to start by drawing a right triangle which has a 45-degree angle in it. So we can start by drawing 2 sides, forming our right angle, and then we're going to draw in the hypotenuse, and we're going to note that we have a right angle and a 45-degree angle. And notice that if this angle is 45 degrees, that means that the other angle is also 45 degrees, due to the fact that all 3 angles in a triangle need to equal 180 degrees. Also, because this now makes this an isosceles right triangle, that is, what we notice is that the sides opposite the 45-degree angles have to be equivalent. What we can do is let the lengths of these legs of the right triangle equal 1. Now let's find the length of the hypotenuse. To do that, what we can do is again use that Pythagorean theorem. We're going to have c squared equals a squared plus b squared. In this case, we're given the values of a and b, and we're trying to solve for c. So we'll have c squared equals 1 squared plus 1 squared. C squared is going to equal 1 plus 1, which is 2. And taking square roots of both sides of the equation, and taking only the positive value for c, we come up with the square root of 2, which is now the length of the hypotenuse. So notice that in relation to the 45-degree angle, we notice that the side opposite the 45-degree angle has a length of 1. The side adjacent to the 45-degree angle has a length of 1. And the hypotenuse has a length of the square root of 2. Now let's use these lengths in order to find the 6 trigonometric functions. We're going to begin by finding the sine of 45 degrees. Again, this is equivalent to the side opposite divided by the hypotenuse. We have a length of 1 for the side opposite, and the hypotenuse is square root of 2. Next, we'll find the cosine of 45 degrees. Our definition gives us the side adjacent, which has a length of 1, divided by the hypotenuse, again, the length of square root of 2. To find the tangent of 45 degrees, we end up taking the side opposite, which has a length of 1, divided by the side adjacent, also has a length of 1, and we can note that this is equivalent to the value of 1. To find the cosecant of 45 degrees, we're going to take the length of the hypotenuse, which is the square root of 2, and divide by the side opposite, which is equal to 1, giving us a value of square root of 2. To find the secant of 45 degrees, we take the length of the hypotenuse, square root of 2, divided by the side adjacent, 1, and that gives us square root of 2. And to find the cotangent of 45 degrees, we're going to take the length of the side adjacent, which is 1, divided by the length of the side opposite, which is also 1, and that gives us a value of 1. Now, let's find these values using a calculator. And what we're going to do is begin with the main three trig functions, sine, cosine, and tangent, which you'll find keys for on your calculator. Let's notice, first of all, that we can evaluate 1 divided by the square root of 2 and find out that that's approximately equal to 7/10. Let's also evaluate simply the square root of 2 to find out that that's equivalent to approximately 1 4/10. Now, we're going to keep in mind those values since we had found those particular values out for the different trig functions for sine, cosine, tangent, secant, cosecant, and cotangent. Let's now go to the calculator and ask the calculator to give us a value for sine of 45 degrees. One thing that we want to note is to make sure that on our calculators we're in degree mode. And so notice if we press our mode key on this calculator, we notice that we have degree mode highlighted. Next, what we're going to do is evaluate the sine of 45, and because we're in degree mode, we know we're working in 45 degrees. To evaluate that, we come up with our value approximately equal to 7/10. Remember that we had evaluated sine of 45 degrees as 1 divided by square root of 2, and this was the value that it was equivalent to. We can also evaluate the cosine of 45 degrees to come up with, in this case, the same value. And the tangent of 45 degrees is equivalent to 1. And we could double check these values with the values that we had found previously. Now, before we end up looking at the other relationships, we need to notice something about the relationships between, for instance, sine and cosecant. Let's look at this. We notice that, by definition, the sine of theta is equal to the length of the side opposite divided by the hypotenuse. We know that the cosecant of theta is defined as the hypotenuse divided by the length of the side opposite. Now, note that these two fractions are reciprocals of each other. And for that reason, what we can notice is that in order to evaluate the cosecant of theta, we can take the reciprocal of the sine of theta. Likewise, if we look at the definitions for cosine and secant, we can note that the secant of theta is equivalent to 1 divided by the cosine of theta. And also, one other reciprocal which is going to help us out is the fact that we can evaluate the cotangent of theta by using the reciprocal of the tangent of theta. So keeping these three reciprocal identities in mind, we're going to use the calculator in order to evaluate the other three trig functions. Let's begin by evaluating the cosecant of 45 degrees. We'll have 1 divided by the sine of 45 degrees, and that gives us our value of approximately 1 4/10, which is the same value that we came up with when we evaluated square root of 2. Let's now evaluate the secant of 45 degrees, and we'll do that by looking at 1 divided by the cosine of 45 degrees, which again gives us this value, which is approximately 1 4/10, or square root of 2. And now let's evaluate the cotangent of 45 degrees by taking the reciprocal of the tangent of 45 degrees, which gives us our value of 1. Now, we're going to use these trigonometric functions in order to solve for a missing part in a right triangle. And here's the example that we want to use. Let's consider this triangle where we're given an angle of 32 degrees. We're given a value of x, which is on the side opposite that angle, and we're given a hypotenuse of 75 feet. In order to use the trigonometric definitions, we need to pick out the one that's going to help us. So again, we've given an angle, a side opposite, and a hypotenuse. Notice that we can evaluate this by using the sine trig functions. So we can write down the sine of 32 degrees is going to be equivalent to the length of the side opposite divided by the length of the hypotenuse. And here we're just going to write down 75, keeping in mind that we're working in feet. In order to solve for x, we can multiply both sides of this equation by 75 to give us 75 times the sine of 32 degrees equals x. Now, let's use our calculators in order to come up with an approximate value for this particular expression. We're going to take 75 and multiply times the sine of 32 degrees, and we come up with a value of approximately 39 7/10. What we can do is actually round this off to the nearest hundredth and write down our answer as x is approximately equal to 39 74/100 feet. Now, the next thing that we'd like to consider is an application where we're going to be using these trigonometric functions. Here's the example that we want to use. 100 feet from the trunk of a tree on level ground, the angle of elevation of the top of the tree is 35 degrees. Estimate the height of the tree. We're going to begin this problem by drawing a picture. And so, we're going to start off by thinking about a tree, and I'm just going to do a quick sketch here of a tree. And with this tree, we'd like to estimate the height of it. So I'm going to take a vertical line straight up, and we're going to then, the tree is on level ground, so we're going to extend, forming a right angle. We have then a right triangle when we connect these two vertices. Notice that we're given some information about lengths. We know that we're 100 feet from the trunk of the tree on level ground, so we're going to draw in our right angle here, and we have 100 feet as this horizontal length. We're also given that the angle of elevation is 35 degrees. Now, the angle of elevation is an angle formed with the rays where you're going to use the horizon, which is this horizontal, and what's called your line of sight, which in this case would be from this vertex to the one at the top of the tree. So therefore, the angle that we're considering here is this one, 35 degrees. We're trying to find the height of the tree, which means we're trying to estimate this length, which I'm going to label with an x. Now, we're going to solve for this value of x by using a trigonometric function, which is appropriate. Notice we're given an angle, we're given a side opposite that angle, and we're given a side adjacent to that angle. That calls to mind the definition for tangent. So we'll write down that the tangent of our angle, 35 degrees, is equivalent to the side opposite, which has a length of x, divided by the side adjacent, which has a length of 100. To solve for x, we're going to multiply both sides of this equation by 100. That gives us 100 times the tangent of 35 degrees is equal to x. Now, we're going to use our calculators again in order to come up with an approximate value for this. Let's take 100 and multiply times the tangent of 35 degrees. We come up with a value which is approximately 70 feet. And so we can write down this as x is approximately equal to 70 feet in height. And the tree then is approximately 70 feet tall. Now it's your turn to try a problem. We're going to look at an application, and what we'd like you to do is to stop the tape and to attempt this problem on your own, and then start the tape back up and we'll look at a solution together. Here's your problem. When the string of a kite is 84 feet out, the kite flies at an angle of 26 degrees from the vertical. How high in the air is the kite? Now, let's look at the solution together. We're going to begin by drawing a picture. Here we're told that we have a kite which is flying, and we're told the angle from the vertical. So let's begin by drawing a picture where we draw the vertical. We're going to then draw what would be the string of the kite, and we're trying to find out how high that kite is in the air, so we're interested in finishing this off as a right triangle. So the height that we're going to be looking for is here. We have our right angle. We're told that the kite flies at an angle of 26 degrees from the vertical, so the 26 degrees will be in our triangle here. And we're told that the string of the kite is 84 feet out, and the string of the kite would be the hypotenuse of this particular triangle. Again now, let's consider which trig function we will use in order to evaluate this h. Here we're given an angle, we're given a side adjacent to that angle, and we're given the hypotenuse. The trig function that we can use is cosine. So we're going to take the cosine of our angle, 26 degrees. That's going to be the length of the side adjacent, h, divided by the length of the hypotenuse, which is 84 feet. To solve for h, we're going to multiply both sides of the equation by 84. That gives us 84 times the cosine of 26 degrees equals h. Again, let's evaluate this using our calculators. We're going to have 84 multiplied times the cosine of 26 degrees. That gives us an approximate value of 75.5 feet. And we can write that down then. H is approximately equal to 75 5/10 feet. And so we interpret this to mean that the kite is approximately 75.5 feet in the air. Now let's finish this lesson by defining some terms and by looking at some related formulas. And the formulas that we're going to be interested in have to do with complementary angles and cofunctions. If alpha and beta are complementary angles, then the following relationships hold. The sine of alpha is equal to the cosine of beta. The cosine of alpha is equal to the sine of beta. The tangent of alpha is equal to the cotangent of beta. The cotangent of alpha is equal to the tangent of beta. The secant of alpha is equal to the cosecant of beta. And the cosecant of alpha is equal to the secant of beta. Notice that what we have are complementary angles. If we think about the prefix co, that's where we use the idea of sine and cosine, having to do with those complementary angles. Now, let's look at what we mean by cofunctions. For cofunctions, what we're considering is the fact that we can find the sine of an angle theta by figuring out the cosine of its complementary angle, 90 degrees minus theta. Likewise, the cosine of theta is equivalent to the sine of 90 degrees minus theta. The tangent of theta is equivalent to the cotangent of 90 degrees minus theta. The cotangent of theta is equal to the tangent of 90 degrees minus theta. The secant of theta is equal to the cosecant of the complementary angle, 90 degrees minus theta. And the cosecant of theta is equal to the secant of 90 degrees minus theta. Let's try an example where we're going to use these cofunctions. The first example that we want to consider is to evaluate the cosecant of 52 degrees. What we're going to note is that the complementary angle of 52 degrees can be found by taking 90 degrees and subtracting 52 degrees from it. That's going to give us a value of 38 degrees. And therefore, we can evaluate the cosecant of 52 degrees by evaluating the secant of 38 degrees. Now, the secant of 38 degrees is equivalent to the reciprocal of the cosine function. So we'll have the reciprocal of the cosine of 38 degrees. We can then use our calculators in order to come up with an approximate value, and let's do that now. We're going to take 1 divided by the cosine of 38 degrees, and that's going to give us an approximate value of 1.269, or 1 and 269 thousandths. We can write that down then as our approximate value. As a second example, let's consider finding the cotangent of 65 degrees by using cofunctions. We're going to note that this is going to be equivalent to the tangent of the angle which is complementary to 65 degrees. Again, to evaluate that, we take 90 degrees and subtract 65 degrees from it in order to come up with a value of 25 degrees. So the tangent of 25 degrees is equivalent to the cotangent of 65 degrees. Again, using the calculators, we can find an approximate value. We'll have the tangent of 25 degrees, and that gives us an approximate value of 466 thousandths. And we can write that down then as our value for the cotangent of 65 degrees. Now, in this lesson, we've looked at trigonometric functions of right triangles. It's time now for you to try some problems on your own.